Okay, so let's do an actual example of how we can set up an integral in polar coordinates. And so first, we're just going to start with an arbitrary function, f of x, y. So let's get my double integrals here. We're going to do it two different ways. And my function, we're just going to leave here. Now, f of x, y, and normally we'd have this f of x, y, dA. If I'm going to switch to polar, first I can switch my integrand. So this is going to become r cosine theta, r sine theta. And then we know dA in polar is going to switch to r dr d theta. And then we're going to figure out our bounds. So we're going to have this exact same integral for both parts. So let's copy that. And then we'll set up the bounds. Okay, and then let's get to the region. So this is just in the first quadrant, and we're going to do the region bounded by the y-axis, circle of radius 2. So let's just imagine that's this piece, x, y, and the line y is equal square root of 2. So we'll put that roughly right there. Okay, so we're actually going to be just looking. This is square root of 2. And this is the region we're thinking of. Okay, let's copy it also on the next, or right over for part B, because it's the same region in both parts. We're just going to think of chopping it up differently. All right, so if we're going to do dr d theta first, this means I am holding theta constant and I'm shooting radially outward. Imagine making a slice of this region where my knife starts and goes radially outward. Actually, let's do it in a different color. It's here. Let's do it in a color where we can see what happens on the limits. Okay. And I'm going to notice where this arrow enters the region, which is here, and where it exits the region. And so where it enters is going to be my lower limit, and where it exits is going to be my upper limit. So where it exits is pretty easy to see. That's always going to be on the circle. So that's going to be exiting when r is equal to 2. It's a little bit harder to see where it's entering in terms of r, right? So notice no matter where I shoot this arrow, it's always entering here along this line. And so notice it's going to enters on y is square root of 2. And I'd like to convert that to see what that is in terms of r. But recall, in polar, y is r sine theta. So this is actually telling me this enters when r is equal to square root of 2 over sine theta, which is square root of 2 cosecant theta. And so that'll be my lower limit here. And then I need to figure out what is the largest and the smallest theta value where I could shot this or make my knife go out radially. And so it's easy. I think it's pretty easy to see that my largest theta value is just going to be pi over 2. But it's a little bit harder to see right away what my smallest theta value is going to be. So we actually need to figure out exactly what that, in terms of theta, what that value is right there. And the easiest way I can get that is by thinking of this is really caused by the intersection. This point right here is the intersection of the circle and the line. And I can find that intersection either in terms of Cartesian coordinates or in terms of polar. So let's do it in terms of polar. It's the intersection of the circle and the line. The circle is r is equal to 2, and the line is equal to r square root of 2 cosecant theta. That's what we just found above here. And so if I solve this, this is going to tell me that at the intersection point, theta is equal to pi over 4, because you get cosecant of theta is 2 over square root of 2, which means my theta ends up being pi over 4. Okay, so that's if I wanted to set it up this way. Now let's think if I wanted to do it the other way. So now I'm going to take my knife and I'm going to keep theta constant, and I'm now going to draw my knife in these little radial shapes, right? So I'm going to be drawing them like, really I'm doing it like this, but I'm just going to start going through my region with these little radial slices. Oops. Okay, so let's just look at one of these slices. How about the one in the middle? And I'm going to look at where this would enter and exit my region in terms of theta values. What's the theta there versus here for this fixed r? So we can see the top theta pretty easy. The top theta is just going to be pi over 2. Now I need to figure out what the bottom theta would be, and notice it's changing depending on where I'm making my slice. So it's not always going to be the same theta. This theta would be different than the theta. And when I'm talking about what theta this is, I'm thinking of in polar coordinates. I'm just trying to think of what color would be easiest. Let's do this. In polar coordinates, I'm thinking of what's the theta associated with that point. So right there, I'm looking for that theta. But notice if I were to start my slice over here, I'd have a different theta. And so my slice, or my theta, is going to depend actually on where I'm starting my slice, and that depends on which r I'm using. And so let's see how that plays out. We're basically just going to use the fact that I'm always entering along the line y is square root of 2, and we're going to convert that now in terms of theta. So instead of what we did over here where we solved for r, I want to know what theta value will that always give me. And that's going to tell me that I have sine of theta is square root of 2 over r, and that means I have theta is arcsine of square root of 2 over r. So that's going to be my lower bound. And so obviously, this would be a nightmare to actually do my integration with these particular bounds. If you're thinking like, well, how the heck would I integrate? I'm just trying to give you an example of how we could set it up for 2 different ways over a given region. Depending on what's in your integrand and depending on what your region looks like, one order may be easier than the other. Typically, I always just try this ordering A first, the dr d theta. And if for some reason that doesn't work, I go to this d theta dr. So this is kind of my last resort. Hence, if you're freaking out about arcsine being in the lower bound, I mean, I tried to pick an example where it was going to be somewhat tricky so you can see exactly how it would work out. Okay, now let's go to our limits. So now what I need is the smallest and the largest r. So again, we're thinking of r as these, it's actually r is just the distance from the origin in this case. So the smallest and the largest r values on this region. And we can see my smallest r occurs here, and that distance is just square root of 2. And my largest r is just the outside of the circle, which is just 2. Okay. So again, I tried to make that kind of messy. Let's go back now to our warm-up where it wasn't such a messy region and see how we can use this idea to convert to polar and actually evaluate this integral. So if this was that part of the mountain that we were trying to deal with during the warm-up, it was too messy. We couldn't actually do it in Cartesian coordinates, but now we're going to switch to polar and see how this all falls out. So take a minute, put this on pause. Based on what we've done so far, see if you can switch this into polar and do the integral, and then we'll talk through it. Okay, so I would say first, you definitely want to draw the region of integration. And since we did this in the warm-up, I gave it to you, but let's actually just resketch and remind ourselves how we do that. So This was telling us that I'm shooting an arrow. This dy is saying shoot an arrow parallel to the y-axis, anywhere between x is 0 and x is 2. So I'm going to shoot it, let's just say right there. And it's telling me it enters the region along y is equal to negative square root of 4 minus x squared, because that's the lower limit. And it exits the region along y is positive square root of 4 minus x squared. And I'm going to do the same thing anywhere for x values between 0 and 2. So that's exactly how we get back to the semicircle. This is my smallest and my largest possible x value. Okay, so this is the region, and we're just reiterating how we could find that given this info. And now we're going to translate this into polar, or convert to polar. So first we've drawn the region, that was step 1. Now we're going to determine the limits of integration in terms of polar. So to do that, I'm going to redraw it because I'd like to make the slice a new way. So let's go down here. Here's the region, and here's this. And now I'm going to slice. Let's decide which way we'd like to do it. Like I said, I always like to do dr first if possible. So let's get it set up that way. I'm going to slice radially outward from the origin. So fixing theta, for a given fixed theta, draw this, and we're going to look at where it enters and where it exits the region. It enters when r is 0 in this case, and it exits when r is 2. And then I fan this like a little sprinkler over the region, and I see what's the largest and what's the smallest possible theta values I could have. And we can see my smallest is negative pi over 2, and the largest is positive pi over 2. I'm not using 3 pi over 2 for my lower bound because we're going to set this up so that my lower bound is always smaller than my upper bound. We're not going to set this up the other way around. So just, you can use whatever theta is necessary so that that will work. Okay, and then I'm going to convert my integrand. So that's step 3. And so here, notice that I have negative x squared minus y squared. If I'd like, I can do this the long way, and I can just literally plug in. Let's do it down below. E to the negative x squared minus y squared is e to the negative r cosine theta squared minus r sine theta squared, which is going to just end up being e to the negative. I'd have r squared cosine squared minus r squared sine squared. I can factor out the cosine squared sine squared, and I just get this. And we could have seen that too if you recall that x squared plus y squared is just r squared, and I just have the negative up there in the exponent. Okay, so this was the long way. You don't really have to do it that long way here. I was just showing you where it's coming from. You can look at it and just say, okay, that's e to the negative r squared. And then I need and maybe we should have done that first, actually. I kind of like doing this first, this r dr d theta piece. So remember that dy dx, if I switch to polar, it's not just dr d theta. And that comes from the picture that we were showing. Let's actually go back and share that picture. I think it's on a different, Okay, so this is the picture I was looking for. This is actually exactly showing you the integral we're trying to integrate from the warm-up. And we're looking at the fact that one of these little areas of these polar subrectangles, it's not just going to be dr d theta, because it changes as I move out in r and it gets larger. So we have found, let's go back to our notes here. That it will be written as r dr d theta. Okay, so Now we can actually do this integral, and it looks way better than before because I now have this the r down here is going to make this integral doable because now I can use u sub. And even better, I can actually decouple this double integral because I am integrating over in polar coordinates what's a polar rectangle, right? And you'll notice that because all of my limits are constants. So when all of your bounds here are constants, and I can write my integrand as a function of r times a function of theta, I can decouple this double integral into just the part that depends on theta. I'll just call that d theta here, and just the part that depends on r squared dr. And then we can do this integral. This one's just going to end up being pi. This one, we can do the u sub. I'm doing it just in my head. E to the negative r squared from 0 to 2. And that's going to give me pi times negative 1/2 e to the negative 4th plus 1/2. If I'd like, I could factor out this 1/2 front. Let's just rewrite it here so that I'm just getting 1 minus e to the negative 4, and I factored out the 1/2. And so that was well, that's actually the only way we can do that integral is by switching to polar. Okay, so let's try a couple more. Next,